Hi friends, let's move on with the very uh, with very continuity of the previous talk that I have had about the Bohr-Einstein debate. Now, in this part, we will move on. We will move on to Neil Bohr. I mean, the quantum atom, and it was the beginning of the scientific revolution. So this will reflect our part two of this video. So welcome back. In the previous part, we saw that by the beginning of the 20th century, classical physics had begun to show the cracks, as we rightly said about it. We rightly talked about it. And Max Planck had introduced the revolutionary idea of energy quanta. And at the same time, Albert Einstein had proposed that light itself sometimes behaves as if it's made of tiny packets of energy, whom we call as quanta. But the biggest mystery was still waiting. What exactly is an atom? I mean, for centuries, philosophers they had imagined atoms. They had imagined atoms as tiny, indivisible building blocks of the matter. Now, by the late 19th century, scientists had discovered that atoms were not indivisible after all. They contained smaller constituents. And then came one of the most important experiments in the history of science. Uh, I mean, the New Zealand-born physicist Ernest Rutherford. What he did, he fired positively charged alpha particles at an extremely thin sheet of gold foil. And based on the accepted model of the atom, the particles should have passed almost straight through the atoms. And most of them did. And a very tiny, I should say, a very small number of alpha particles bounced back almost directly towards the source. And Rutherford was astonished, and he later remarked that it was surprising as firing a cannonball at a sheet of tissue paper and having it bounce back at you. The conclusion was unavoidable. Almost all of the atoms, mass, and the positive charge must be concentrated in an incredibly tiny central nucleus. And what was proposed? The electrons occupied the surrounding space. This was truly a magnificent discovery. But at the same moment of time, yet it immediately created a serious problem. And according to the classical electromagnetism, if you have any charged particle moving in a curved path, it should continuously lose electromagnetic radiation, because there is acceleration in the charge, and an accelerated charge will always produce electromagnetic radiation. And an electron orbiting the nucleus should therefore lose energy every second. As it lost energy, its orbit should keep on shrinking within an unimaginably short time. The electron should spiral into the nucleus of the atom, and the atom should collapse. But the world around us uh, it's clearly, it does not collapse. I mean, every chair, every mountain that we have, every tree that's surrounding us, every human body consists of these stable atoms. And nature itself was telling scientists that something fundamental was missing in classical physics. That might be the right argument. Now, this is where we have this young Danish physicist whom we know as Niels Bohr, a genius. And Niels Bohr entered the story. And in 1913, Bohr proposed an idea that initially seemed almost unbelievable. And what this genius suggested is that electrons are not allowed to orbit in any arbitrary distance from the nucleus. It cannot choose any of the paths while spiraling around the nucleus. Instead, there are only certain specific orbits that are permitted for this electron to revolve around the nucleus, and these are called quantized energy levels. What am I trying to tell you here is that imagine there is a staircase, okay? You can stand on the first step, you can stand on the second and on third. You can stand on the fourth, but you cannot stand halfway. Between two steps, you cannot stand anywhere. Similarly, according to Bohr, an electron cannot possess just any of the energies. It can possess only specific energy. Step 1, step 2, and step 3. These are what we call as allowed energy levels. Now, at the very first glance, this sounds very strange. Why should nature impose such a restriction to the movement of the electrons? And Bohr did not have a complete answer to this question. And what he did, he proposed this rule because it successfully explained the experimental observations. Sometimes science advances by discovering the pattern that are surrounding you, discovering these patterns. Before, before fully understanding what's going on and why those patterns exist, Bohr further proposed that while an electron remains in one of these allowed orbits, it does not radiate energy, which is completely against the classical theory of electromagnetism. And what it does, it emits or absorbs energy only when it makes a transition from one energy level to another energy level. And the energy of that photon is equal to the difference between the two energy levels. This is beautifully explained. Uh, uh, this beautifully explains basically the spectral lines of hydrogen atom. And for the first time, physicists could actually calculate the exact wavelength of light. The wavelength of light that's emitted by hydrogen atoms. And those calculations matched experiments with astonishing precision. So you are picking some reality from these experiments and you're translating these realities into equations. The Bohr model was not perfect, that's clear. It worked exceptionally well for hydrogen, but it certainly struggled with more complex atoms, the atoms that have more than one electrons. Nevertheless, it marked a turning point. What it did basically is it demonstrated that quantum ideas were not mathematical curiosities roaming in a pure kind of mathematics, but they described something real about nature. Now, another question emerged. If electrons occupy these strange quantized states, what exactly electrons are? Are they particles or are they waves? This question became even more puzzling in probably close to 1920s. And here we have the French physicist whom we know as Louis de Broglie. And Louis de Broglie proposed a remarkable idea. What he did, he suggested that if light, which he had long been considered a wave, can sometimes behave like particles, then perhaps particles can also behave like waves. This was an extraordinary, bold proposal given by Louis de Broglie. Now, according to de Broglie, every moving particle possesses an associated wavelength. At first, this seemed almost impossible. It didn't match to the thoughts of the pupil. It seemed almost impossible to believe. How could something as solid as an electron also behave like a wave? Yet science is guided. It's guided by experiments, not intuitions. Your intuition can prove to be wrong. So soon afterwards, experiments confirmed the de Broglie predictions. When beams of electrons were directed towards a crystal having ordered atoms or molecules in it, they produced diffraction, they produced interference patterns, and the unmistakable signature of wave behavior. The evidence was overwhelming by bombarding these electrons on a crystalline substance. So electrons were neither ordinary particles nor ordinary waves. They exhibited characteristics of both, being a particle as well as a wave. And this phenomenon became later on known as wave-particle duality. So you had the duality for light, now you have duality for particles. Now let's pause and think about how extraordinary this really is. What am I trying to tell you is that imagine you throw a tennis ball towards a wall with two narrow openings. Okay. Now, the common sense, what does the common sense tell us? The common sense tells us that the balls must pass through either the left of the opening or the right of the opening. You have two narrow holes. It should either go into the one or into another. The ball cannot pass through both the holes at the same point of time. I mean, the ball cannot pass both the holes simultaneously. Now imagine replacing the tennis ball with a beam of electrons. Now, if you do not observe, I mean, which opening each electron passes through, an interference pattern gradually appears on the screen. You have the interference pattern showing the wave nature of electrons behind the wall. The pattern is exactly what waves produced. It's as it's as though each electron behaves like a wave. And this wave is spread. This wave is spread across the space, passing through both the openings of the wall. Now, before arriving at the detector, yet when the detector finally records the events, it always registers a single localized electron. Now, how can something travel like a wave but finally arrive as a particle? This was no longer a philosophical puzzle. It was an experimental fact. The deeper physicists investigated the the so-called microscopic world of atoms, molecules, electrons, and protons, the stranger nature appeared. Now, by the mid of 1920s, we have a new mathematical formalism, a new mathematical starting equation, a new mathematical framework was being developed. And it was Werner Heisenberg. And Werner Heisenberg introduced matrix mechanics. Soon afterwards, we have Erwin Schrödinger. Erwin Schrödinger developed wave mechanics. Now, at first, these two approaches seemed completely different. Werner Heisenberg's matrix approach and Schrödinger's wave mechanics approach. Now, later, it became clear that they were both mathematically equivalent descriptions of the same quantum reality. And this was one of the greatest achievements of theoretical physics. One of the finest, one of the beautiful one, the great one, the loved one. So quantum mechanics had arrived. But this new theory introduced an entirely different way of thinking. Now, instead of predicting the exact future motion of every particle, quantum mechanics predicted probabilities. Now, instead of saying the electron is definitely at this point, it described the probability of finding electron at this point. Wherever is the maximum probability, the chance of finding electron is maximum. I mean, the electron can be at different locations. This represented a profound departure from classical physics. So for centuries, scientists had believed that if you knew the present perfectly, you could calculate the future perfectly as you know the initial conditions of your problem. But now you have a mathematical framework supported by experiments. Quantum mechanics challenged that belief. At this point, Niels Bohr began developing one of his most influential philosophical ideas, the principle of complementarity. Now, according to Bohr, wave behavior and particle behavior, they are not contradictory. They are basically complementary of each other. The description is complementary in nature. Which aspects appears to depend on the experimental arrangements. So nature is not basically changing. Our experimental questions determine which aspect of quantum reality is revealed through a particular experiment. This was radically new philosophy, and many physicists accepted it because it successfully explained it successfully explained the experiments that people were performing in the laboratories, and others found it deeply unsettling. And among those who remained unconvinced was one of the founders of, I should say it, one of the founders of quantum theory himself. And the man was the genius Albert Einstein. Even Einstein admired the extraordinary predictive success of quantum mechanics, but he never denied the experimental accuracy of this theory. But in heart of his hearts, he believed that the theory was incomplete. He suspected that beneath the apparent randomness, there should exist, beneath this randomness lay a deeper level of reality. And that deeper level of reality, uh, level of reality uh, was yet to be discovered by the physicists. This difference in the scientific philosophy would would soon lead to one of the greatest intellectual confrontations in the history. The world's finest physicists would gather. They would gather in a series of famous meetings known as the Solvay conferences. There, Einstein would challenge quantum mechanics again and again with brilliantly designed thought experiments. And each time, Neil Bohr would respond